Hello, my name is Dr. Cristina Hickman, and today I'm going to be discussing strategies to optimize culture in time-lapse incubators. So my disclosures is that I am the Vice President of Clinical Affairs for Fertility. I am also the Chief Scientific Officer for Apricity, a lecturer at Imperial College London, a consultant for IVF professionals, and a co-founder of Ara Fertility, a clinic in London. There are a range of time-lapse equipments available in the market that are in use in IVF labs. And these vary according to their capacity, the type of dish they use, the type of optics that they use as well. I have had a lot of experience using time-lapse. I was using big box incubators back in 2010. We then moved into the planar incubator. The benchtop incubator. And then it wasn't until 2011 when I was at Care Fertility that I first had the experience of using the ESD, the embryoscope. In 2013, I built the first clinic worldwide designed around the time-lapse technology because it became clear to me that the workflow that we were using was going to completely change when using time-lapse compared to not. And in 2014, we made sure that all of our patients were using the embryoscope. We were actually one of the first clinics worldwide to offer time-lapse systems for all of the patients. I also have experience with other systems. So in 2016, we installed the Jerry. We had the first Jerry pregnancy in the UK. And in October 2016, we installed the first Embryoscope Plus post-validation. And this was also at Boston Place Clinic. More recently, in 2020, I've taken the latest advances, not only in time-lapse, but also in digitization and artificial intelligence, to create a new clinic in London called Ara Fertility, which is designed around using the digitization to enhance patient care. And it has been quite a journey. It's been a lot of fun because we were the first at using a lot of these different aspects of time-lapse. We kind of had to figure out how to use it as we went along. And we learned a lot in the process of what are the best strategies that should be incorporated for us to maximize the benefits that this technology brings, not only our team, but also our patients. And this journey has been going on now for over a decade. Back when we were just using morphology and we realized that, morphology as an embryo selection tool wasn't enough. We've done quite a few presentations worldwide looking at the morphokinetics and determining which morphokinetics we should be considering or not, looking at what are the right statistical methods to be using to extract from going from data to decision-making tool, whether we use central statistics, then we moved into outliers and clustering. We then started using absolute time points or maybe interim time points. We went into a range of different types of models, from hierarchical models to multiplicative models to universal models. And then we started thinking about, wait a minute, annotation takes a lot of time. And these manual annotations, we need to figure out how we get consistency in this. How do we improve our definitions, our quality control? How do we get to the point where we have guided annotation and even completely automated annotation? We also then started looking at our workflow and completely modified the way that we prioritize tasks in the lab. And in that, we identified efficiencies that led to bringing a reduction in cost to our practice. And ultimately, not just about improving success rates, but we also looked at how we can use this technology to improve the patient journey and the patient experience. So let's go through these one by one. The first one is the workflow. What are the strategies that we want to consider in order to improve the lab efficiency and consider how we can bring a reduction in the operational costs? So Alikani published this in 2013, where she laid out the multi-steps that we have in a traditional embryology lab. And it's quite complex what we do, that there are multiple moving parts that we need to kind of be on top of to make sure that at the end there's a baby for the patient. And in fact, by the introduction of time-lapse, we were able to eliminate a vast majority of these steps. Not only were we able to remove some steps, but the steps that were still left for us to do, we had a lot more flexibility in how we perform them. So for instance, the time of when we're going to do our stripping or our for ICSI or for IVF, the time that we do our day one checks, our observations, when we call the patients, when we do our biopsies, how do we determine the optimal time to biopsy the embryo based on the expansion of the embryo? Having access to our time-lapse systems from outside the clinic so that we can better manage the workload accordingly. And all of these together led to less weekend work overall for the team, less staff required, and an improvement overall in work efficiency. We went as far as to look at the financials behind this, and time-lapse is an incredibly expensive technology to incorporate into your lab. But what we found was that when you adapted your practice to what the technology brings to you, and when we take into account all of these savings that come from this adaptation, we found that at least in our clinic in London, it saved the cost of the equipment was counteracted by the financial benefits within 1 year. So in a way, the technology paid for itself in monetary terms. When we're looking at the time-lapse system, it's really a CCTV of the embryo. It's taking pictures of the embryo as it is developing. And these are pretty pictures, but somehow we need to go from pretty pictures to decision-making. So how do we turn images into an embryo selection tool? So the way that we do that is by a process called annotation. So what we do is we convert the images into biologically relevant data that is either continuous or categorical. So in a way, we move from a picture to numerical forms that we can now process. And these numbers are extracted from the phases of embryo development or features that we identify in the embryo. And there you have the absolute time point that these features happen. So for instance, the T2 is the time of the first division. T3 is the 3 cells and the 4 cells and the 5 cells and the blastocyst formation and expansion and the hatching. So all of these can be taken as absolute time points. But we can also look at in-between time points where we're looking at the pace of embryo development. We can look at the pace of embryo development as a ratio at different stages of embryo development. So this now creates our cell cycles. And we can look at the synchronization of these cell cycles. And although these are mathematical numbers, they have biological relevance in terms of ensuring that the embryo has sufficient time or is not spending too much time to go through the cell cycle checkpoints that it needs to go through to ensure a viable embryo at the end. So we took these numbers, and so here's an example of an absolute number, the second division. In blue, you have those that led to a baby, in red, the ones that didn't. And initially, when you look at the central statistics, you can see that they have exactly the same central statistics. But what we found is that when we start looking at the outliers, we start seeing a lot more negatives and a lot fewer positives. So it was very clear that although the central statistics were the same, the outliers were very different. And this goes across all the morphokinetic parameters where you have these ranges where it's outside the norm. And when you bring that together with the interims, and we now can create decision trees to make, to accumulate all this information to something that we can process, this is what came the models, the time-lapse models. And from 2012 to 2014, there were a range of publications where different models focused on different stages of embryo development. We also have not just models, but looking qualitatively through the video, where we're trying to identify unusual cleavage patterns, for instance. So on the left, you have a direct division 1 to 3, also referred to as ducts in the publication. And on the right, you have the reverse cleavage. So the direct division 1 to 3 is when it goes from 1 cell to 3. That's not normal. It's supposed to go from 1 to 2. And that's a bad sign in terms of viability of the embryo. Reverse cleavage is when it starts reducing the number of cells. Okay, so in this case, it goes to 2 cells, and then it increases to 3 cells, and then it goes back to 2 cells again. That, again, is not normal behavior for an embryo. And all of these biologically relevant parameters are listed in the ESHRI guidance on good practice recommendations to the use of time-lapse technology that came out in 2020. So this is something that if you're using time-lapse, I would suggest that you have a look. And in fact, it has gone as far as defining all of these parameters so that we have consistency and definition. But I just wanted to show you the sheer amount of parameters that are coming, that have been acknowledged by this publication. And in fact, there are many more which have come out after 2020. So we have, for instance, the example of the ratio of the inner cell mass, the trophectoderm. We have the pattern of collapse and how this is also predictive of implantation and so on. So I became very interested in, wait a minute, I have tried to figure out how to use time-lapse because, you know, we were amongst the first, but how did everybody else figure out their way of practicing? So what I did was I traveled around the world in over 20 countries, in over 250 clinics, and I visited the clinics myself one by one to understand how everybody interpreted their particular practice. And these are some of the differences that I identified. So one of them was which piece of information did each clinic actually use to make their decision. The clinics that were really busy tended to only use the last image and just make the determination with normal morphology. They completely disregarded the rest of the information that came from time-lapse. Other clinics, so the second group, they would annotate, and they would take time to annotate their videos, and they would use potentially either absolute or interim modules that they build algorithms themselves in their clinic, or algorithms that were commercially available. In the third group, they were really focusing on the qualitative. So they'd be looking at whether the divisions were normal or not in terms of, is it reverse cleavage, is it direct and even cleavage? They were looking at the collapse and the re-expansion. They're looking at multinucleation. And they're making determinations only on that and ignoring the annotations. And then there's a fourth category where you're looking at the complete information, and all three are taken into consideration. And in fact, the increase in efficacy or prediction kind of increases as you go down this list, but your efficiency reduces. So the more time you spend extracting numbers out of your time-lapse videos, the better it is in terms of efficacy, but you're making yourself, it's very time consuming. And sometimes we're just too busy and we just can't accommodate this logistically. So just to give you an idea on the distribution, morphology only was a minority of clinics, 7%, and really half the clinics were looking at the qualitative side. There were no clinics that were looking at all of it. So I also asked a lot of these clinics how they annotated, which embryos do you annotate clinically? And this was another strategy to try and make it efficient in the lab, where either they annotated all the embryos, which is extremely inefficient, or they would only annotate on those which are clinically relevant. So for instance, only good quality blastocysts, or only embryos that are being considered for transfer. And the rest would be ignored or annotated at a later time point when there was more time. So all of these differences are things that we need to consider when we're strategizing how best to use our time-lapse system. But we have to acknowledge there's so much information coming from the time-lapse. How do we process all that information? And this is where my interest in artificial intelligence came from. So artificial intelligence is really the marriage between computer science and mathematics. And it's created a whole range of tools that will help us achieve efficiency, classification, and prediction, not on a few bits of information, because this is all we can process as a human being, but in the entirety of the video, the entire information that comes from the time-lapse system. Ultimately, we can use AI to help us achieve more time-efficient ways that are also consistent, more predictive of outcome, and in a way reducing risk and error of our processes. So this is one example from fertility, which is one of the team that I've joined recently. And effectively, you can see on the left that the AI can pick out all of the features which we were before trying to annotate manually. So it sees the pronucleates, it sees each of the cell divisions, and in fact, it does that in a higher degree of accuracy than us humans. So not only is it faster, but it's also more accurate. And in doing that, we can also pick out little bits of information we've never had time to look for. So not only is it identifying the inner cell mass in the trophectoderm, it's actually telling you that this, according to Gardner grade or Asabir grade or whatever grading system you use, it's telling you what is the grade it suggests it is. Not that it's telling us what to do, but it is helping us. We are there. We're the ones still in control, and we can just use this to make our life more efficient. But if we disagree with the machine, we override it. We are always there driving it. And ultimately, all that information now can be used to make the decisions we need to make. Are we going to discard this embryo, or are we going to freeze it? Are we going to transfer as a single embryo transfer, or are we going to transfer as a multiple embryo transfer? And the idea is that we don't make these decisions based on opinion. We make these decisions based on fact. So all of these methods of embryo selection that we see in our lab. So traditionally, we have the morphology, the time-lapse, and the PGTA, right? And these have different pros and cons in terms of invasiveness, in terms of consistency of determination, in terms of whether it's too expensive to incorporate to all our patients, the instantaneous aspect of whether you can get the results right away or whether you've got to wait a couple of weeks as you do with PGTA, and whether it's predictive of outcome at all. And in fact, we are involved in quite a few projects that are assessing these, including the non-invasive PGTA and the artificial intelligence. But the benefits that come from the AI is that when used in conjunction with the other methods of embryo selection, it is instant, it is cheap, it is consistent, and it is non-invasive. And these are very important parameters when trying to choose your strategy of how to select the best embryo for transfer. So one of the things that we've seen is in this workflow, you can see the various stages of that we have in our lab. So all the processes that we have to go through. And what I'm highlighting here are the various commercial companies that are currently available to help us make the clinical decisions, because it goes beyond embryo selection. We do have oocyte assessments, we have sperm assessments, and all of this kind of comes together using artificial intelligence to support us throughout the fertility journey in the lab. So what are some examples of using time-lapse and artificial intelligence to save on time? So this is a workflow that when you're incorporating time-lapse for the first time, you might want to rethink what are the tasks that are done on different days. And the ones that are highlighted in blue can be streamlined even further because these can be automated using artificial intelligence. So Amy Barry, which is the head of laboratories at Care Fertility, she did an assessment of the fertility system for automatic annotation of embryos. And what she found was that the level of agreement between what the experienced embryologists did the annotations and what the Fertility Kids Plus system did in automatically annotating was very similar and was in fact above a strong level of agreement. So this demonstrates with a very experienced time-lapse group that artificial intelligence can effectively take over some of the roles, which in a way are quite administrative, right? We didn't become embryologists to do annotations of embryos. We became embryologists to be in a decision position of which embryo to transfer back. So the idea is that using artificial intelligence with time-lapse, we spend less time annotating, less time evaluating time-lapse videos, less time doing routine data processing and data cleaning. And instead, we dedicate that same amount of time to communicating more detailed information, more personalized care directly to our patients. And empowered, we're able to do this because of artificial intelligence. And we can also use this extra time to now create new options of what to do with this data. For instance, trying to predict when a problem is going to happen. So instead of using KPIs such as fertilization or KPIs such as pregnancy to see if there's a problem operationally in your lab, we can now use more sensitive biomarkers that come directly from your time-lapse system. So ultimately, by incorporating these technologies together, we are bringing more babies per embryologist. None of this is to replace the embryologist. This is to enhance our capabilities. So how can we use time-lapse and artificial intelligence together to improve consistency? Well, one of the problems we have in our field is that there's lots of different ways to classify embryos, right? So in my clinic, we use Gardner, but in my friends in Spain, they use Asabir. The Americans use the Vicans and Innovic. Then we have the Istanbul consensus. And, at the end of the day, we're all looking at the same things. We're looking at expansion, we're looking at inner cell mass, we're looking at trophectoderm. And effectively, using these different languages is confusing. It's confusing for communications between labs. It's confusing for patients to understand what is actually happening in their own treatment. Now, even when we are using the same language, the other difficulty we have, and we presented this in a Nature paper, is the fact that when you give the same information, so in this case, 395 images, and we give them to 5 different experienced embryologists from different countries, they only agree with each other on the Gardner classification in 1 in 4 of these. So this inter and intra-operator consistency needs to be improved. Why are we having these difficulties in grading embryos across different embryologists or within the same embryologist on different days? It's because we're using our human eye, and the human eye is subjective. So here's an example, which is the Ebbinghaus illusion. When you look at these 2 green dots, the bias of what's around the dot will make you think that the one on the left is smaller than the one on the right. When in fact, if you remove the bias, you can see that they are exactly the same size. And this is directly related to how we're classifying blastocysts. And in this particular example, how we're classifying the inner cell mass. What is around that inner cell mass is going to cause bias for her on whether we think it is A, B, or C. And it's not just what is around it, it's the fact that the inner cell mass has different shapes and they come in different positions in the embryo, whether it's on the side of the embryo or on the bottom of the embryo. And we tend to have a bias classifying better quality. The inner cell masses are positioned on the side compared to on the top. So the way that we currently classify our Gardner embryos is that we have these definitions. But these definitions, like many cells, tightly knit, or few cells, or very few cells, I mean, these are very qualitative, right? And this leads to subjectivity. It is fast and it's simple, and that's how it's been designed. But that subjectivity is not really appropriate for a clinical decision-making event. The Asabir has recognized this, and they have now created a new grading system where they have specific dimensions and number of cells to determine whether it's an A, a B, or a C. And this is great because it brings objectivity to the decision. And so it's really tackling that problem. But at the end of the day, it is complicated. It's slow for us, because for us to be measuring each of our embryos and counting the number of cells is much slower than just having a quick look and see as we do with Gardner. And therefore, the slowness and the complicated aspect makes it difficult for us to incorporate this into clinical practice. So this is where artificial intelligence comes in, because you can now be fast, be objective, and be simple. Okay, and on top of that, we also have the ability to capture additional information that we wouldn't have had time or ability to collect. So this is where the new biomarkers come in that we would never be able to do ourselves, but with a computer, we can now personalize the care even further, not to each patient, but to each individual embryo. So here's one project that I'm working on at Upper City. It's led by Peter He. He's one of my PhD students, and he's looking at, look, when you get the images from the time lapse, you have the different focal planes, and we have, and these are stacked together, as you can see for this particular embryo. What he's doing is he's taking the focal plane above and the focal plane below, and he's asking the artificial intelligence, tell me what the focal plane in the middle would look like. And you can see in the bottom that the predicted one, the one created by the artificial intelligence, and the one who is real life, the truth, are actually very similar to each other. Now, what he can then do is he can keep asking that question again and again and again, and create an endless number of focal planes, which he can then reconstruct together to put together the 3-dimensional image of this particular embryo. Okay, so now we can, not only artificial intelligence, we're now going into the realms of virtual reality, where we can turn the embryo It's not physically being turned. The embryo is still safely in the time-lapse incubator, but now we can turn the embryo to try and figure out what's happening, not only with each individual embryo, but with each cell in each individual embryo. Okay, and this can now be tracked using AI throughout the embryo's development to give us a whole new dimension of morphokinetic parameters, which are specific to each cell. We have created new classification systems which would never be able to be incorporated by humans, where we're looking at not only how many cells there are, but how are they positioned relative to each other? What is the shape of the embryo overall? And in fact, there are many shapes that are possible for these cells to form relative to each other. We're also looking at how tightly each cell is connected to each other, because this gives us an idea of the intercellular communication. And we are able to measure the intracellular distance from each individual cell. So whether these have biological relevance or not is going to be next step, and just watch this space. Another thing which is very important, ultimately, we're all doing this, all this embryology here is for the patient. We're not doing it for the embryos, we're doing it for the patient. And therefore, we cannot just focus on the time-lapse effect on the embryos. We need to take that extra step of how can we use this technology, not just to improve success rate, which is very important, but also to improve the patient engagement. And what we've done is we've interviewed the lab directors in the UK, and we asked them to tell us, do you give the patients the videos of the transferred embryos? And you can see that there's a difference in practice, but the majority of the clinics do provide the videos to the patients through a USB. And there's also differences at what point of the treatment the patients get these videos, with the majority providing these at embryo transfer. So at Boston Place, one of the clinics that I built, we did it through the reports that were automatically generated by the time-lapse system. And we had the USB where we would sit down just before transfer and show them their embryo. Good news or bad news, we would use the embryo to educate the patient on the implications of transferring this particular embryo on this particular patient. We asked the lab directors whether they gave copies of the reports. And not all of them did. In fact, the majority didn't. And this is something that hopefully will change in the future. I believe in ultimate transparency to the patients, and I want to get to the point where the patients have access to the videos live so they can see what we can see. Okay? And this is a very common practice here when you go to a restaurant where the cooks are cooking in front of the whole restaurant. We can see where the burger is coming from. We can watch, and this brings trust between the patient and the IVF lab. And this has actually been put in practice by a number of clinics around the world. One example is Institut Marquez. And their experience, they've actually quantified the experience from the patients and found that all of the patients through the questionnaires demonstrated that seeing these images live was a very powerful and calming event for them. It didn't increase anxiety. It actually created the opposite effect. It was a positive experience overall. And they weren't obsessed looking at the videos constantly. They only looked at them 3 to 4 times a day. Okay, so this is something that we should all be considering. And then how do we improve the prediction? So there's a number of publications now in PubMed. There's a number of publications which are specifically looking at use of artificial intelligence. Now, the majority of them have been on static images, but we're seeing more and more focusing on time-lapse. And the idea is that the more information you are processing through artificial intelligence, the more likely it is to be predictive of the various outputs, such as ploidy or pregnancy or live birth. And we do see differences in terms of how these metrics of how they are proving whether this works or not. That really requires some standardization at the moment. But the common theme throughout is that when they're comparing AI with humans, where these comparisons have taken place, they very much have demonstrated the improved consistency that comes from artificial intelligence. And this has been unanimous across the papers. In terms of does AI improve over human, the amount of improvement will vary according to a number of factors. And one interesting factor that I wanted to highlight is the level of seniority of your embryologist, or the level of experience. So the more experienced you are, the less improvement AI brings to you. So what this does is it brings consistency in determination of which embryo to transfer back across your entire team, irrespective of the level of experience. And I think this is a great thing for a patient, because it is unfair that a patient will have different success rates depending on the seniority of the embryologist choosing which embryo to transfer back. So I think this is a fantastic benefit that artificial intelligence brings to our field. We've also looked at several other strategies and differences in practice when I was visiting the different clinics around the world. And one of the things that came up is that when to culture the embryo in the time-lapse system did vary. And some clinics, maybe they didn't have capacity for all their patients. So maybe their fairness was to apply time-lapse only for the initial stages of embryo development. And that was it. They then removed from the time-lapse system in order to give space to the next patient. But really, ultimately, if you want the best strategy for your patient, it's to maximize the amount of time that this embryo is in the time-lapse system. So you want to be thinking of strategies such as short IVF instead of overnight IVF. You want to be thinking about immediately after ICSI, it goes into the incubator, and it stays in that incubator until the point of either vitrification or biopsy or transfer. And in doing so, you can now maximize the information, particularly on that first day of development, from day 0 to day 1. And it's not just the formation of pronucleates that we're looking at. There's a whole array of biological events that you will be missing out on doing the overnight IVF incubation. The other thing to consider is to look at the timeframes of the entire process, including the HCG trigger for your egg collection. And, keeping it all the way to blastocyst for all the patients would also be important. So if you're doing a lot of cleavage transfer, this goes against bringing out the best benefits that come from time-lapse and AI systems. You really want to have a consistent practice when all your patients are going to blastocysts, and ideally including day 7, not just day 6. So if you're interested in AI and you're interested in fertility, Zaninovic, Velimir, and Rosawak and myself have put together a conference, which is the AI Fertility Conference, to be held in Dubrovnik in September from the 15th to the 18th. So really hoping to see a lot of you there. Thank you very much for your time.